Okay, so next, let's talk about how to use deep learning to address the computer vision problems we mentioned before. We will use 4 examples, in the following pages for this part, to illustrate how to apply deep learning to address these problems. So the first problem we have mentioned before is how to use deep learning to address the image classification problem. Now we can use the CEM model we mentioned before. We have introduced this before already. Given one image input, we can build one CEM model to classify the image into different classes. So inside the CEM model, given the image input, we have convolution layers as well as pooling layers, which will be able to learn the features from the input image, right? And based on the learned features, we can further flatten this feature tensor into one vector and feed it to the Fourier connection layer, which will be very similar to an MLP model. And which will be, and based on this Fourier connection layer, we can classify the image into different classes. So we have covered this already. We can use one CEM model to classify the images into different classes. Besides image classification, we can also use the image localization with this with CEM model as well. So we have a new variant of CEM model. It's called regional based CEM model, which was proposed in 2014. So the RCN, or the region-based CEM, can perform the selective search to extract multi-high quality region proposals on the input image. So we can choose a pre-trained CEM and truncate it before the output layer. In other words, given one input image, like this one, we can extract different regions inside the image. We can propose different potential regions, of course. For example, given this image, we can propose now 2K different regions, right? And then we can further feed each region, in the proposal into one CEM model, which has been pre-trained already. What is pre-train? Pre-train means we can train one CEM model with some other data sets. Now we have some other image data sets which has human beings, has horse, has different other objects. We train the CEM model first, right? We train the CEM model first. And however, then based on the pre-trained CEM model via some other data sets, we can transfer the pre-trained model here and insert it into this architecture. In other words, for this pre-trained CEM model, given any input data, then we can apply a CEM to it, right? However, the main concern here is because these proposed regions will have different sizes, and the size can also be inconsistent with this pre-training CEM, right? So to make the size of the input to be consistent, then we can do some reshaping of the image, right, or the regions in the image. Like this rectangle, we can resize it into a square instead by shrinking the dimensions of the images, right? And then we can feed this resized regional proposals into the CEM model, into the pre-trained CEM model, and do the classification of these objects. So by the pre-trained CEM, we can classify the regions we fit into the model, right? In other words, for all the proposed regions, we can classify them into different classes. So in this way, we can classify different regions in the input image into different classes. And we can furthermore be identifying whether this region will be precise for some objects or not. So you can see for the image localization, what we do is to enumerate different combinations of different regions in the image and classify them into different labels. Right. If for some region, if we can classify them to belong to one certain of the regions, then we can know. This region is about one object, right? In this way, we can know. Which area are about certain objects. This seems to be very stupid. However, for computer vision, we have no better ways. So for human beings, our eyes can precisely know this region is for this person, right? However, for the computers, it is very hard for them to know this region actually. We have to enumerate different regions, then we can find a region which can be identified by the pre-trained CEM model. Okay, so this is the way we do the image localization, and then we can use this region-based CEM model to do the localization of the objects inside the one image. And besides this method, right now, in recent years, we also have seen some other new models which can further improve this region-based CEM, because this one will be very slow. We have to enumerate different proposal regions in the input image. There will be some other methods to speed up the learning process and to extract the region more precise and to narrow down the proposals and to speed up the learning process. And besides the localization, we also have talk about how to do the transfer of the image styles before, right? If you still remember when we discussed about autoencoder model, we have mentioned how to transfer the image from one style to another, right? And if you still remember, we can transfer the image like this dog, according to some styles, into a new image instead, like this one. It is still about one dog, however, its style is very similar to the style we provide instead, which will be very different from the input image. And we also mentioned how to use deep learning to do the image style transfer. With the CEM model as well as autoencoder this framework, we can build one model to transfer the image style from one to another instead. Now here, given one autoencoder model, we have an encoder as well as decoder, as shown here. Right? Now we can use CEM as an encoder and DCEM as a decoder. So given the input image, we can learn some features from the input image, which will be like this one, right? And these features we extract from the image can be combined with some style information we extract from a style bank. Now each style will be one image as well. From them, we can extract some features as well via some models like CEM or another CEM instead. So this style information together with learned features can be fed as input for the decoder, like the DCEM, right? And from the DCEM, we can generate some new images which cover both the original image as well as some new styled images according to the style we provide, right? So it depends on how we define the loss function. Then the model can learn different outputs, which can both reconstruct the original input and also can generate some new styled images outputs as well. So you can see, via deep learning, we can also do the image style transfer as well, which will be very interesting, and you can try it by yourself. I think there should be some source. I think this code has been open source already, and you can download the source code provided by some other authors and other researchers, and also do the transfer of the style by yourself out of class.